So this morning when I woke up, I took a look at the GFA and I also took a look at the TAF, and both of them showed that it was supposed to get pretty windy today. In fact, that's supposed to happen any... Hey, I can hear them picking up already. Whoa, that's getting to be strong. Whoa, yo, oh goodness, whoa, oh bother. Okay, whoa, okay, they were also supposed to slow down very quickly. But anyways, okay, there we go, they're calming down now. So right on schedule, just like the TAF and GFA said. Anyways, in this section, we're going to take a look at winds. And those beautiful palm trees, you can definitely see they're encountering the effects of winds. We don't really have palm trees in Canada, but anyways. Okay, in this section, I'll admit it's going to be a little bit long. And that's because winds are fairly complicated, but they're also very, very important to us as pilots. Winds can have huge effects on, say, our takeoff and landing performance. They can also have huge effects on our ground speed as we do across country. Winds can also have huge effects on our performance when we're landing and taking off on approach and departure. Say cases where we have wind shear, increased, decreased performance. So because winds are so important, it's really important that you understand how they work. They're going to have huge implications on you and your flying every single day. Now, of course, on the exam, there's going to be lots of questions about winds, how they work, and as well, practical questions on the exam as to how they could potentially influence your flight. So maybe get comfortable and let's start to delve into winds. Now, we're going to start out with the most simplest little bit of theory when it comes to winds, and we'll constantly build on it, getting more and more complicated. At its core, the basics of how winds work are pretty simple. Let's say that we wake up and we have a weather person who starts to draw on their weather map, and they discover that, well, over here I've got an area where the pressure is high, and over here I have an area where the pressure is low. What will happen is because the pressure is high here, the winds will start to flow towards this area where the pressure is low. This is something known as the pressure gradient force. Now, what I want to do is, having given you that most simplest bit of winds, we're next going to explain how it is that these pressure gradient forces develop. And in order to do that, I'm going to go over to the whiteboard. But just before I go over to the whiteboard, let's keep it simple to start. What is wind? The movement of air in the atmosphere. Horizontally, this is the most common way we as pilots experience these winds. As I just pointed out, winds are caused by horizontal pressure differences. Air will typically move from an area of high pressure to an area of lower pressure. Now, what creates these differences in pressure? It is actually related to temperature, believe it or not. And here's where we start to go a little bit more complicated by looking at winds in 3 dimensions in a simple form on the whiteboard. So let's head over to the whiteboard now. All right, so let's first of all imagine 2 columns of air that are exactly the same in every respect. So we're going to draw these 2 columns of air. So you can think of them as containers full of air. I like to, as I said, think of them as columns of air. Now we'll make these 3-dimensional columns of air. With these 2 columns of air, what we are now going to do is we are going to start to fill them. So, same height, same width, and then, of course, we start to fill them with air molecules. We're going to say that maybe we put 5,000 air molecules in this column, and we put 5,000 molecules of air in this column. Both of these columns of air are at the exact same temperature as well. All right, so let's draw these two columns of air stretching up into the sky. And perhaps most of us, since we are pilots, we would like a little airport here somewhere. A little hangar, and then a nice little taxiway to go to the hangar there as well. So as we know, this column of air with all these air molecules is going to put pressure downwards upon the surface of the Earth. So that being the case, we can imagine all of these molecules pushing down at the surface of the Earth, and if we were to take our barometer and measure it, we would find that it's 2,992. Okay, standard atmosphere. We're going to imagine that this is 15 degrees Celsius. Sure, sounds good. And then over here, of course, since it's exactly the same column of air, 2,992, 15 degrees Celsius, well, all that weight, exactly the same column of air, right? So I'm just going to erase these pressure points because in a few moments we're going to modify things a little bit. Now, what I want you to do next is imagine that these two columns of air stretch and reach up to the 3,000 foot level. So there we go, 3,000 foot level right there. So from here to here, this is 3,000 feet AGL. We'll say that this is at sea level right here, this airport. So we could say 3,000 ASL. So there's our 3,000 foot level. Now, if everything is exactly the same, we have a happy situation where there's no wind. However, we're next going to imagine that in this column of air here, a farmer suddenly comes out, and that farmer decides, well, you know what? I think it's a good idea for me to maybe go out there and plow my field. So that being the case, the farmer comes out and plows a field there. Okay, so now what's going to happen? Well, of course, we've got the sun up here, and if you remember our discussions on temperatures, well, you're going to say this land over here, because it's nice and black, over here, perhaps we have a nice little green soccer field or something like that. So you're going to tell me that this here is actually going to start to warm up, and you would be exactly correct. So this then goes from 15 degrees Celsius, and it starts to warm up. So let's say it's only by 1 degree to 16 degrees Celsius. Well, now what's going to happen? A couple of things, of course, are going to happen. This is warming up, so that means the air molecules near the field are going to warm up, and they're going to start to rise through the atmosphere. Up they go. Now, as the air in this column warms up, the easiest way for it to expand is upwards. So it starts to expand slightly above the 3,000 foot level. So there we go. We'll draw this extra little box showing this expansion of this column. Now, both columns still have the same pressure at ground level, 2,992, 2,992. They still have both 5,000 molecules, right? So that's why the pressure stays the same. However, I want you to look now at the 3,000 foot level. And let's say, because of the rising air molecules, that let's say, I don't know, maybe 10 air molecules, just to keep things simple, end up in this box above the 3,000 foot level. Well, at this level, 3,000 feet, can you see what's happened now? We have an imbalance. I mean, over here at 3,000 feet, there's 0 molecules. Over here at 3,000 feet, there's 10 molecules. So do you know what the air says? It says, hey, wait a minute, there's an imbalance. So what it starts to do is the molecules in this box above 3,000, they say, hey, wait a minute, I've got to move over to 3,000 feet in this direction over here, and the 10 molecules here start to move over here. So instead of 10 being here, those slowly wander over in this direction. And guess what happens over here now? 5,000 minus 10 gives us 4,990 molecules left over here. That's after these have migrated. Now, there's an additional 10 molecules over here at the 3,000 foot level, so this means that this ends up with 5,010 molecules. So initially, what we had at the 3,000 foot level, we had high pressure here, because remember, there were more molecules above 3,000 feet than there were over here at 3,000 feet. So we had the air move from an area of high pressure at 3,000 feet to an area of low pressure at 3,000 feet. But that messes things up at the surface now, because there's 5,010 molecules here suddenly. There's only 4,990 molecules here, so that means there's more weight pushing down in this column. So guess what happens? In this case, 2,900 or say maybe 2,994. Meanwhile, as these 10 molecules leave, the pressure over here drops to, let's say, 2,990. So at the surface, here's what I have. 2,994, this would be a high pressure area at the surface. Over here, this is going to be a low pressure area at the surface. So guess which way the air is going to flow from the columns at the surface? In that direction. So what you can see now is we have generated a circulation. First off, it starts in the upper levels, the high to the low, because of that imbalance. This, of course, these molecules in here are going to sink down towards the surface, creating extra pressure, and now there's going to be too many here, so they're going to move over here, and we have that perpetual circulation starting to move now. All thanks to this farmer out here who plowed his field. Okay, so what we've seen from this diagram here is the differences in pressure creating that wind. All right, so thanks to our farmer, well, of course, it's going to be differences in temperatures throughout the Earth's surface. We end up with temperature differences, which create pressure differences, which create a force that will cause the air to move from a high to a low pressure area. Now, when a meteorologist wakes up in the morning, what they're going to do is at the surface, they're going to start to find all the various pressures. And notice here that these pressures we have listed in what are known as hectopascals. They will then start to connect all these areas of equal pressure. So 1020, I got 1,020 hectopascals here. So I've drawn a series of lines connecting these areas of equal pressure. Once I do this, I get something known as isobars. These are imaginary lines which join points of equal pressure, specifically mean sea level pressure. Now, once I've done this, I'll notice that the isobars can sometimes be close together and they can sometimes be far apart. Now, first of all, let's look at this just a little bit closer, and just like that last slide, we can see 1,008 hectopascals. This is the lowest area that the meteorologist has found, so we've stuck a low here. Moving in this direction, we can see that the pressure increases in terms of hectopascals, and up here somewhere, just off the chart, we have the highest area of pressure, so that would be where we would stick a high pressure symbol. Overall then, the air is going to be flowing from the high towards the low. Now, as we draw these isobars, what you can see is there are locations here where the isobars are closer together than, say, over here. These isobars can indicate to us as pilots where there are areas of high winds. Remember that term, pressure gradient force. The closer together these lines are, the higher the pressure change is, which means the winds must flow faster through those zones. So, pressure, as we've been learning, is measured in hectopascals. Now, sometimes you may accidentally hear the terms millibars. That's because we did use those in Canada up until fairly recently, and in the US, they still use millibars as well. So sometimes if you hear the term hectopascals or millibars, they're actually pretty much interchangeable. They're the same in terms of their amounts. So Canada use hectopascals, but once in a while you might hear millibars, and don't be confused by that. When it comes to these isobars, just like we saw in that last chart, notice that they are drawn in 4 hectopascal intervals. Important that you know this for the exam. As I mentioned, Transport Canada uses hectopascals when publishing weather charts. It's important to also remember, as I mentioned previously, that these are all in terms of mean sea level. Remember that the standard ISA sea level pressure is 1,013 hectopascals. All right, that's the ISA. Remember, we're going to have 15 degrees Celsius, technically going to be dry air, and as well we also have the standard lapse rate. So this diagram here is another example of showing you the pressure gradient and its effect on winds. Pressure gradient is technically the rate of change of pressure over a distance. It's indicated by the actual spacing of the isobars. And it makes more difference to the weather than the actual values that we see here. I'm going to come back to this statement in just a moment. What you need to remember when it comes to reading a weather chart, if the pressure gradient is strong, the isobars will be close together. If the isobars are close together, then the pressure gradient is steep and it's producing strong winds. Okay, so this term here, pressure gradient is steep, so that's where they're tightly packed. Just like right here, we have strong winds right at that location. Now, here we've got a distance of 200 miles, and in this case, as I look at the pressure readings, I can see that the difference is 4 hectopascals. So this here, from C to D, would be a shallow pressure gradient, which means the winds would be relatively calm. Specifically, when compared to this distance here, only 70 miles from A to B, we can see again a pressure difference of 4 hectopascals, but in this area here, the winds are going to be stronger. Remember, we're also going to have overall that pressure attempting to go from the high towards the low. We'll come back to getting this a little more complicated in just a little bit. But I want to come back to this statement here for just a moment. This statement here is kind of important because when I wake up in the morning, if I'm a meteorologist, and I start to connect all of these lines of equal pressure, whether I call it a high or a low is something that's kind of subjective, because some days an area that I might mark as a high, a few days later, I actually might mark it as a low, even though the pressure is the same as a few days ago. You might be scratching your head a tiny bit. So guess what? It's time that we go right back to that whiteboard to show you how this works. As an example, I'm just going to leave this here, but this diagram here doesn't have much to do with the diagram that I'm going to draw just below it. For instance, one day, as a meteorologist goes about plotting their nice little sets of isobars, they discover that this particular high maybe has 1013. And you're like, well, Aaron, that's standard. How on earth do we assign that a high or a low? Well, 1013 is just the standard, right? Over in this direction here, the meteorologist identifies a low, and as they mark all of the isobars, they discover that this low is maybe 980 millibars. Okay, so very definitely the meteorologist says, here's the high, here's the low, and now has a rough idea as to which direction the winds are going to go. Now, the next day, the meteorologist goes out and measures two different areas, or actually the exact same area, but discovers that today, well, all right, so here's day one, and then over here is day two. So the very next day, the meteorologist measures the same spot. And as they measure the same spot, they're like, okay, well, today it's like 1024 here. So connects all of the isobars, and then they measure over here, and they see, oh, it's 1013. So now what's going on? 1013, well, it was a high over here, but now if I compare the two, I'm like, well, this one's definitely the high pressure today, no doubt about it, compared to over here where it's only 1013. So we got to tell this one that it's the low, even though it may have seemed that the day before, 1013 was a zone of high pressure. All right, so high versus low pressure is subjective. I don't want you to get into your head that 1013, something higher than 1013 is high, something lower than 1013 is low. Not necessarily. As you've just seen, switching from day one to day two, that can be subjective as they're measured one to the other. All right, so pressure really depends upon the pressure surrounding it for any given day. Remember, the overall flow of the air is going to be from where the pressure is high to where the pressure is low. Now, that starts to get a little bit more complicated, actually. And guess what we're going to do next? We're going to start to look at some of these complications in terms of this high moving towards the low. First off, before we do that, let's look at a practical example now of the pressure gradient force and these tightly packed isobars by looking at a GFA. So down in the lower left-hand corner here, I can see this area of high pressure. It's looking like it's at a maximum value of 1,025 hectopascals. From there, I can see these isobars connecting, and you can see that these are definitely 4 hectopascals apart. Up in the upper right-hand corner, oh boy, do I ever have a bad batch of weather here, located around here with this low. Okay, now, as we move towards the low, let's imagine that I was an aircraft taking off and I'm flying towards this low. I'll notice that the isobars are far apart here as I leave, and then as I get closer and closer and closer to the low, look at how packed these isobars get. So I'm going to expect very, very strong winds as this pressure gradient becomes steeper. And sure enough, I can actually see these winds marked right in here. Like, look at this, 30 gusting 40. I've got right in here, 25 gusting 35. So right in here where they're most packed, notice how the speed of the winds is the strongest. As they become a little bit more separated again, I can see that the winds slow down just a little bit, although 25 gusting 35 is still very, very strong. Now, remember, in the simple examples that we've given previously, remember, we said the winds are going to flow from the high and they're going to fly towards the low. But what I want you to notice is this. Look at these wind barbs here. Can you see how these wind barbs are actually showing that, well, the wind doesn't flow directly from high to low, Aaron? You told me they do. Yes, I know. That was to keep things simple so that we could start to move towards the more complicated things to see how the winds actually move in the real world. So at the surface, what I want you to notice is that the winds are not quite parallel to the isobars, but they're bent a little bit to the left of the isobars. You can very clearly see that as you look at this isobar here, and then you look at the wind, and you can see the direction, so eventually it would hit the isobar at an angle. So it doesn't flow directly towards the low. However, at the surface, it flies at a slight angle to the isobars. That's at the surface. Notice as well the overall flow around the low. You can see here as you copy all of these winds, see how the winds circulate counterclockwise around the low. Around the high, we can see that the winds flow clockwise. Okay, so around the high, they fly clockwise, but always at a slight angle to the isobars at the surface. Now aloft, they flow differently. We're going to start to look at winds aloft. What I want to next do, though, before we do that, is we're going to introduce a term known as the Coriolis force. Now, in order to understand the Coriolis force, we once again need to consider a simplified model of the global circulation of air. Remember that first whiteboard diagram exercise that I gave you, where I showed you that temperature differences would create pressure differences at both the surface and at a higher altitude? Okay, for the Coriolis force, for us to understand this and how it modifies the winds, causing the winds to flow at a slight angle to the isobars on the surface, we need to once again look at a simplified model. The first model we're going to look at is what we would call the single cell model of Earth circulation. Notice the pole here, and eventually we have the equator. Well, remember, warm air here at the equator, that's going to be constantly rising if we think about it in a simplified term. As we get to the pole here, what we're going to have is colder air that's going to be sinking. The term here is subsidence. Now, what I want to do is I want to go back to the whiteboard because I want to show a better picture of the air rising at the equator, where it is heated through it's heated and it rises, so we call this convection. So that causes an area of low pressure near the equator, and then traveling up to the poles, losing heat as it goes, will advect that air towards the poles, and then we will subside at the pole. And then from there, it will go along the surface and come back to the equator. So let's go over to the whiteboard for a few moments and take a look at a simplified single cell circulation model of the Earth. So before I erase this, I want you to take a quick look at this and remember this. Warm air starts to expand. Cooler air is a little bit lower. And then we have that circulation happening, surface versus aloft. Okay, so let's look at the simple circulation cell for the Earth itself in terms of what the atmosphere is doing. All right, so we'll draw as best as we can a fairly close to circular Earth. I need to make sure that I get this big enough. Oh, that's not even close to a circle. But anyways, I'm sure you get the idea. So what's going to happen is we're going to have the North Pole right here. And then, of course, we've got the South Pole here. All along this, of course, we've got the equator. Now, let's imagine that we had those two ideal columns of air, one at the equator. So again, this one we can imagine has those 5,000 molecules in it. And then what we did was, again, we put that same one at the location of the pole. I'm sure some of you can kind of guess where this is going already. Think about the poles and all of the snow and ice there. Well, of course, this air is going to be fairly cold. This air here, of course, is going to be fairly warm. We've got all of that warm air at the equator, and what's happening, of course, is that warm air starts to get going, and it's like, hey, it's time to rise into that atmosphere. So what's going to happen is initially we started out with these two columns being the same. So let's draw our imaginary height. And in this case, I'm going to use my imaginary height as being 20,000 feet. So there's 20,000 feet. Initially, prior to the air warming, both of those columns are exactly the same. But now, the air at the equator is really warm, so it starts to rise. And as we've seen, what now happens is this column of air then becomes slightly bigger. Well, now what's going to happen? Got the rising air through this column, continues upwards, and it's like, hey, wait a minute, we've got more air molecules up here than we do at the pole. So guess which way this all starts to flow? Well, you've seen this before, so you know that the flow is going to go like that towards the pole. Meanwhile, this pole starts to fill up with extra air molecules, it starts to sink and get heavy, and it's like, wait a minute, now at the surface, it's really extra heavy, but there's not as many molecules over here, so now we get this cold air flowing along the surface of the Earth towards the equator again. So this is an idealized model, and this is what we call the single cell model. The single cell model doesn't happen with the real Earth. And that's because next up, we've got this pressure gradient force, right? Pressure gradient force there, then we've got a pressure gradient force down towards the bottom as well. What we have is we have the Earth rotating. So it rotates from left to right according to the way that you're looking at it. And as this Earth rotates, what happens is this wind that initially starts flowing directly towards the poles actually suddenly gets bent in a certain direction. And that would be to the right. So as all this air gets bent to the right, and it's like, oh, I can't go to the pole. What actually happens is we have a buildup in here at about 30 degrees north. Okay, I want to stop there because what I now want to do is start to go into the Coriolis force and what it's doing. Remember, right now we've got the single cell model. In a few moments though, once you start to learn about the Coriolis force and what it does, we're going to move over to the tri-cell model. That's coming up next. Okay, so that's the first part of our simplified single cell model of the Earth. Now, this is starting to lead to, in greater detail, the Coriolis force right here. So we've seen how the air circulates, moving from the equator, advecting upper air toward the poles, subsiding, and then coming back to the equator. Things get a little bit more complicated, though. They don't just simply flow straight north and straight south. You have to remember that these winds are moving over a rotating surface, specifically the surface of the Earth, which, as we know, is spinning as it orbits the sun, and that spinning is what causes day-night, right? Once this air has been set in motion by the pressure gradient force, it undergoes an apparent deflection from its path, as seen by an observer on the Earth. This apparent deflection is called the Coriolis force, and it is a result of the Earth's rotation. Okay, now, the best way that I could think of showing how the Coriolis force actually works is by using an apple, actually. So you can quickly read through these, but what you need to know is that as the air moves from high to low pressure in the northern hemisphere, it is deflected to the right by the Coriolis force. So the Coriolis force causes the air to get deflected to the right. In the southern hemisphere, it's the opposite. It will be deflected to the left. If the Earth did not rotate at all, we would not have the Coriolis force happening. So, Coriolis force here, in the next few slides, it uses the example of a merry-go-round. And this is actually a pretty good example. However, I kind of thought about it a little bit, and I came up with another one that uses an apple. So, once again, here's the principle of the merry-go-round. Somebody, in the middle here, somebody out on the edge of the merry-go-round, and these two people decide to throw a ball to one another. Okay, well, what I'm going to do, if you threw a ball on a merry-go-round, you would see that the ball would appear to be curved to the right if you were spinning the merry-go-round in the same direction the Earth rotates. For us, though, let's actually use a spinning apple to see how it is that the Coriolis force creates this deflection of winds to the right. All right, let's go over to the video then.
Okay, so here we are to demonstrate Coriolis force, and you're like, well, we're not in the studio anymore. Yeah, you're right. You can see I've got an apple here, and then over here what I've got is an apple peeler. Now, this is going to help me demonstrate the Earth's rotation, because what you do is you take this crank here and you turn it. Now, as you turn it, you can see this axis actually spins in that direction. So it spins counterclockwise, which is really handy. I mean, if I take the apple here and I imagine this spinning, it's going to spin like this, which is the exact same direction that the Earth rotates. Now, to peel the apple, this would come down and it will shave the skin off, but we're not going to actually do that here. Now, what I'm going to do is I'm going to put the apple on here, and I have to be as careful as I can to try to get this on as straight as I can, otherwise it doesn't work very well. And then I'll show you what we're going to do next. So right here, I've just got your plain old basic Sharpie. Now the trick with the Sharpie is I'm going to kind of do it from this angle in a few moments, and then what I need to do is imagine that the tip of the Sharpie is a parcel of air. So what's going to happen is this parcel of air is going to start at the pole, and then it's going to move downwards towards the equator while the apple rotates. What I'll then do after showing you that is we'll imagine a parcel of air going from the equator with the tip moving straight up to the pole. So we'll start out with the pole to the equator, and we'll see what would happen if I was a parcel of air and I was moving in that direction. So let's get our Sharpie ready here. I'll just rotate the apple just a little bit. So there's the tip of the Sharpie. It's at the pole. And now, as I mentioned, I'm going to start to rotate this, and I'll pull that Sharpie downwards as I rotate. It is a little bit tricky to do. I'll try my best and we'll see how it works. So just got to make sure I've got good contact with the apple first. So there we go. There's good contact. And let's start to rotate this apple now. So there we go. There's the Sharpie moving downwards as the apple rotates. Okay, well, let's take this off and let's take a look at the path that it followed. Wow. If I'd started right here, it kind of, but you can clearly see it keeps moving off to the right. So that's a pretty good demonstration of how the Coriolis force is making the apple, or not the apple, but the parcel of air move to the right as the apple rotates beneath it. Okay, so let's try this again here. Let's put this back on. I'm just going to change the position of the apple. Oh, that's not very well mounted. I'm just going to change this so it's mounted just a little bit better. It needs to be mounted fairly straight for this to work. So I'll just tilt it just a little bit. Okay, that's not too bad. All right, now let's imagine the reverse happening. And we're a parcel of air that's now going to move upwards towards the pole. So we'll make sure we've got good contact here. There we go. All right, let's start to move the Sharpie upwards as we rotate the apple. Okay, now that actually didn't turn out too badly. It wasn't perfect, but you can see that the overall motion, we started at the equator, right? The overall motion kept turning to the right. Now, the other thing that's worth noting is look at the curve when you've got leaving the pole, look at the curve near the pole, very, very tightly curved, and then look at the curve as we hit the equator. Eventually, the curve is very gentle. The reverse happens at the equator. Initially, the curve is gentle, but then as we get closer and closer to the pole, look at how this curve tightens up significantly. So what we end up with is the Coriolis force has an effect on us that is greater at higher latitudes. So the closer I am to the pole, the greater the Coriolis force is going to be. The greater the speed of the wind, the greater the Coriolis force is going to be. Okay, well that's a pretty good demonstration, I think, of the Coriolis force. So maybe what I'll do is I'll put that right back on there, and then take the shield off, and I'll actually peel this and turn this into something like applesauce or maybe an apple pie. Oh, that would be so delicious, wouldn't it? Well, maybe not yet. But yeah, okay, yeah, somebody could come to the studio and enjoy that. Anyways, we'll go back to the presentation now then.
All right, so now I'm really looking forward to something like maybe, an apple pie, or maybe say an apple crumble or something like that. Yeah, okay, let's move on. So now that you know how the Coriolis force bends winds to the right as it moves, let's look at how this changes the wind flow that we've been discussing. So what I want you to next think about is, we're going to, for a few minutes, ignore the winds on the surface. And we're going to look at the winds aloft. That's because aloft, friction doesn't modify our winds. So we get a true picture as to what is going on. Then, in a little while, we're going to look at how the surface winds are modified by friction. Okay, so we're going to look up high. In the upper troposphere, the air is unaffected by friction. And we can see that there ends up being a balance between the pressure gradient force and the Coriolis force. Okay, stay with me here. So I've just zoomed in on that last slide. Remember, over here, if I draw right here all of these areas where I've got my isobars, so here's 912, look at this. Somebody used millibars. And you know what? I think when I talked about subjective pressures on the whiteboard a little bit ago, I think I accidentally said millibars as well. My apologies. So this must have been from the US, this particular chart. So here we've got all of these, and we can see that they are spaced 4 millibars apart, which is exactly the same as hectopascals. So 912 millibars is definitely more than 900 millibars, which I should have actually said 912 hectopascals is definitely higher than 900 hectopascals. So overall, the pressure gradient force, that right here you can see is marked in red. So what's going to happen is if I'm wind at the high pressure area, I'm going to try to flow directly towards this area of low pressure here. So that's what happens. The pressure gradient force gets the wind moving. Now, as I start moving, however, remember the Earth is spinning below me. So as we saw, just like that apple spinning, what's going to happen now is as I start moving, I'm going to get shoved off to the right. So we can see right here in black that it's actually showing the Coriolis force constantly bending me to the right. Now, as these winds speed up, eventually what will happen is the pressure gradient force will exactly equal the Coriolis force. So what that means is aloft, remember, in the upper atmosphere, what will happen is the Coriolis force, after the winds get going, will force the winds to parallel, you can see here, the isobars. Now, on upper level charts, these are technically going to be called contours, and they will actually be at equal heights. I'm not going to get into that here. We will talk about that elsewhere in the meteorology section here on pilottraining.ca. But what I want you to remember is anytime the winds are at a height of 3,000 feet or more, there is no frictional effects. So what happens is the Coriolis force will cause the winds to flow directly parallel to the isobars. And then you might be thinking, but Aaron, on the GFA, you said that the winds were flowing at a slight angle to the isobars. Remember, GFAs show the winds at the surface. This here, as I look at 900 hectopascals, this is at about 5,000 feet above the surface of the Earth. There's no friction causing anything to happen to these winds. However, GFAs which are at the surface, friction causes the winds to get modified and bent a little bit. We're going to start to discuss that in a little bit. However, for now, know that upper winds always parallel the contours, or in this case, the isobars. All right, so aloft, when we have the pressure gradient force moving the winds, and then we have the Coriolis force forcing them to the right, the wind that parallels the isobars is known as the resultant wind. The resultant wind also has another name that you should remember, and that is the geostrophic wind that blows parallel to the isobars. Okay, so this is at high altitudes above 3,000 feet. Remember that, where friction has no effect upon the winds. All right, so the resultant wind, as we've seen, is known as the geostrophic wind. It is important to remember that the geostrophic wind is the resultant wind at heights approximately 2,000 to 3,000 feet above the ground. At heights less than this, the resultant wind is slightly modified by friction from the surface. I've already told you this. Now, before I go on, though, what I do want to do is actually spend a few moments before we start to talk about friction. I actually want to talk a little bit about something known as the tricellular model. Okay? So, I think what I'll do, I'll quickly read this. We'll read a little bit about friction, but we're kind of jumping ahead here right now. The resultant wind at that height, the geostrophic wind, as those winds get closer and closer to the surface as we move down, friction starts to cause the winds to slow down. So what's happening is, as we slow those winds down, the Coriolis force will have less of an effect on it. they won't get bent to the right as much. So remember the GFA and how we had those winds at a slight angle to the isobars? Right here, we've got that statement. The reduction in the Coriolis force as we approach the surface and friction becomes apparent will cause the winds to flow at a slight angle to the isobars near the surface. Okay, keep that in mind. We're going to come back to this in just a little bit. What I want you to think about, though, next, before we move into the tricellular model, is something known as the Buys-Ballot law. Buys-Ballot was a Dutchman who recognized the existence of the geostrophic wind as early as 1857. His law states that if you stand with your back to the wind, as long as you're in the northern hemisphere here, the low pressure is always on the left and the high pressure is going to be on the right. Remember, we talked a little bit about how around a low, it circulates counterclockwise. You can see right here, this is obviously at a high altitude because I can see that these winds are flowing geostrophically and they are moving parallel to the isobars. Around the high, I've got that right here. So parallel, but clockwise. So if I was standing right here and I put my back to the wind and I stuck out my left hand, well, what I would see is that would definitely point towards the low. So this is kind of handy for us as pilots. Anytime you feel a wind outside, you can put your back to the wind, stick out your hand, and the low is going to be to the left of you. All right. Here's another diagram of that. You can always work out the direction of the resulting wind. You can always figure out where the low is. Now, before we continue to start to get too far into the frictional effects, you remember that simplified single cell circulation model that I showed a little while ago. Air warms up at the equator, rises, moves through advection towards the poles, and then sinks at the poles. It's actually a lot more complicated than that. So what I want to do is I want to next introduce to you the tricellular model. Technically, the Earth's rotation causes this single cell to split up into 3 cells. And what this all means is that there's more than one cell that is responsible for recirculating the air throughout the Earth's atmosphere. Let's go back to the whiteboard and let's start to draw this out then. All right, so a few moments ago, we drew in that single cell model, and then what I did do was I took the time to show you that air starting to get bent off to the right at 30 degrees north. And you can see how it starts to pile up right in this zone here. So what I'm going to do, I'm going to actually erase this, just because now that I'm done with the single cell model, I need to have a slightly bigger diagram so that we can start to view the tricellular model. Now we're going to zoom in on the Earth from the pole to the equator. So I've just made this a little bit bigger, this arc here. I'm not going to draw the whole Earth this time, mostly because I want some good detail as to what is happening with the cells. So let's draw in our equator here. And I'm going to draw in a small zone. So there's the equator. I'm going to draw in a little belt here. And that's because I want you to first of all visualize this air, very warm, moving upwards from the north of the equator, and then as well from the south of the equator. So in an idealized world, what would happen, I'm just going to switch colors here. No, I'll actually keep it red. I just don't want you to confuse these with temperatures though. For now, the temperature idea kind of works because there's the warm air. All right, so now it gets to altitude,
and it starts to move off in this direction. Now, it has cooled as it moves upwards, so don't think of these colors as temperature necessarily, please. Just think of them as the actual circulation. Now, ideally, these arrows would continue flowing in that direction towards the pole, right? However, as we've discussed, they keep getting curved off to the right. And as that happens, it ends up that they start to kind of pile up right in here, and they're like, whoa, we're all now following the geostrophic wind, which is parallel to the isobars. So what they do is they're like, whoa, there's starting to get to be too much pressure in here, and because of that, they're actually forced to move downwards. Now, this happens at about 30 degrees north. So I'm going to draw another zone right in here. So this is 30 degrees north. This is 0 degrees north, the equator. And as this air comes down, some of it's now forced in that direction, back towards the equator, but some of it is forced in this direction. There's so much pressure here that really it has no choice but to move either south or north. So what we end up with is along this zone here, we end up with what we would call more of a permanent high. And this particular high pressure zone causes very clear air. Remember, if air sinks, it's going to warm up, right? So this corresponds, for most of you who notice, in the US, it corresponds with a lot of the desert regions of the US, the very warm regions of the US. This here turns out at the surface of the Earth to be a little bit more of a permanent low. So now all of this air works its way northwards. Some of it does continue to circulate aloft in this direction as well. But now something else is going on. Remember, at the North Pole, again, the colors I'm using are not related to temperature. At the North Pole, this air is happily moving this way towards the equator. Well, guess what happens right here? The northbound air suddenly strikes the southbound air, so guess where it's forced? Upwards. Same here, upwards. We still have that general flow in this direction, and downwards like that. So in this zone here, what I now have at 60 degrees north, I now have an area of rising air. So again, we end up with more of a lower pressure area. So that being the case, guess what's going to happen here in terms of weather? Well, like here, rising air, we end up with lots of rain. Here, it's dry. This is sometimes called the subtropical high. This here is what we would call the polar zone, and this causes the air to rise again. So what we have is we have three cells now. Remember, this flow here is kind of backflowing a little bit as well. It gets quite complicated in this zone, as you can imagine. But overall, the circulation is like this. Overall, the circulation here is like that. Overall, the circulation here is like this. We call this particular cell up here the polar cell. This cell here is called the Ferrel cell. And then this cell here is what we call the Hadley cell. All right, so that is actually what is happening with the 3-cell model. All right, so I know earlier I said to think of the winds aloft. For a moment, I will have to come back down to earth, so to speak. And that's because sometimes people find these questions on the exam as well. Which way, in terms of big scale circulation, are the winds flowing on the surface? Well, let's look at the Hadley cell first. So in this case, if I imagine these winds flowing from north to south, a non-rotating Earth, that's exactly what would happen. They would just flow like that. Meanwhile, with the Ferrel cell, it's just going to kind of flow straight like that. The polar cell is going to flow straight like that. But remember, the Coriolis force has an effect on these winds, and it forces them to the right. So in this case, we would have the winds going from 30 degrees north back towards the equator, kind of like that. We call these the trade winds. Meanwhile, of course, this moving from the subtropical high towards the pole gets deflected like that. So overall, we end up with what we call the westerlies. And then here at the North Pole, we'll again angle those off to the right. These are what we call the polar easterlies. Okay, gets a little bit more complicated than that because we also have something setting in known as friction. Now, for friction, what I first want you to do is come back from the surface and get back up here to the point where we are aloft. Okay, so aloft and where we have the geostrophic winds. Remember, geostrophic winds flow parallel to the isobars. All right, let's go back to the presentation now, I think.
All right, so, boy, winds are complicated, aren't they? We're not quite finished yet, though. The next few slides are mostly a review of the tricellular model that we just looked at on the whiteboard. So here's the cells that we've seen, and here's that circulation. Once again, another diagram showing the equator here and the cells and the circulation towards the poles. The next picture I want to show you, though, is actually one that kind of gives proof of where I said, well, we have the air moving up from the equator, so we get convection going, but then at 30 degrees north, we end up with the air sinking. Remember, as the air reaches the equator, so as it comes from the south and it comes from the north and it gets forced upwards, we have what is known as the intertropical convergence zone. So what's going to happen, of course, is we're going to end up with, look at this, you can actually see in this photo from space, you can see right here very clearly all of these convective clouds right near the equator. Notice as well, remember, this is going to come up towards you, and then it's going to flow out towards the north. Eventually, when we get to 30 degrees north, it starts to sink. And look at here where we said that we can end up with generally clear skies. You can see on both sides of the equator, that's exactly what's happening. As I go further north here, look at how we start to enter that connection between the polar cell and the Ferrel cell. And remember, again, we have rising air. Well, look at all the clouds and weather systems forming in this zone here. All right, so back to the equator, though. Thunderstorms and low-pressure systems abound in the equatorial region. That space photo shows that. So we've talked how the air circulates from there. I've shown you that space photo to kind of show you that, yeah, 30 degrees, clear skies, and stable weather conditions. Eventually, we get to the poles, and remember, that flow returning from the Ferrel cell as well now causes the air to move upwards again. This is the area that we call the polar front. As you saw on the space diagram, we have unsettled weather again. Okay, this next slide suddenly seems to be a little bit out of place because it says veering and backing. All right, now, what I want you to think about for just a moment is the upper level winds. As we move downwards towards the surface, remember how a number of slides ago we said that friction starts to have an effect on these geostrophic winds. So, if I'm a pilot and I'm at a high altitude and I start to descend, the winds, because they're encountering friction, will actually start to slow down. Conversely, if I'm a pilot and I take off from the surface of the Earth and climb, well, the air above me is going to have less and less friction, so it's going to speed up. The other thing that maybe isn't quite as obvious is because of the fact that, well, the Coriolis force doesn't have as much of an effect on the winds near the surface because of friction, these winds are going to change direction. So what I want you to remember for now is these two statements. Veering is a wind direction that changes clockwise. Okay, for example, if I have a wind that is blowing from a direction of 270, and as my airplane climbs, I find that it is blowing from 320, that is veering. Backing, conversely, is a wind direction that changes counterclockwise. Okay, so if I'm in an airplane and I'm at a high altitude and I descend, let's say at that high altitude, the wind was 320. As I descend, I notice that the winds at the surface are from 270. That is an example of backing. Now, as a general rule of thumb, this is the standard way that winds behave. And this could be an exam question because if you find something the opposite when you say study a table of upper wind charts, FD charts, generally speaking, this is the way that things behave. This would be standard. If you don't find this, it's a non-standard wind as you study those tables. Winds will veer and increase during a climb out. Winds will back and decrease during an approach. So keep those in mind. I'm going to actually use the iPad in just a few moments to start to draw these things out so that they make a little bit more sense. In fact, for this next slide, I think I should definitely go to the iPad because I can talk a lot, but I can also draw a lot, and sometimes drawing a lot is a little bit easier to understand. A picture is worth 1,000 words than all of these words here. First off, remember, at 3,000 feet, the wind generally parallels the isobars. The surface of the Earth is going to exert a frictional drag on the air that is blowing just below it, and this will act to change the wind's direction and speed. Okay, so let's pick up the iPad for just a few minutes, and let's actually look at this in terms of three dimensions and a drawing that we've created. So, as we look at this drawing, first of all, we have here the surface of the Earth. Now I can see this surface of the Earth has a nice little ocean here, sea level as we can see, and we can see somebody out here enjoying a calm wind day in their boat. Now, as I move in this direction, I start to move inland. Out here you can see that I've got this vast plain, so maybe this is like the prairies in Canada. As we continue to move on, eventually I start to hit forests and I hit mountains. We'll ignore that the mountains are smaller than the trees. We'll just say that this is rough terrain. Okay, so above us, of course, we have the wind that is howling, the geostrophic wind. So that's represented by this. And you can see how I've shown some of the contours or isobars technically contours at high levels. And I can actually see that my geostrophic winds are blowing from 270, and what's happening is we've got a speed of 20 knots. Now maybe early in the morning, okay, it's nice and calm. In a few moments, we'll start to talk about how these winds can end up coupling with the surface. So in the morning, there's really not a lot of connection between the upper level winds and the lower winds. So it's nice and calm. However, what will happen is eventually these winds will start to work their way down towards the surface of the Earth. Now, remember, initially we start at a very high altitude here, 3,000 feet, where there's no frictional effects. But as I come down 2,000 feet, 1,000 feet, and then eventually the surface, which is sea level, of course, I'm going to encounter some friction. So as I'm moving down, the wind will slow down. The other thing that's going to start to happen is the Coriolis force doesn't have as much effect on it. So this rightward movement is actually going to start to spin this way, and it's going to become slightly left of the isobars, angled slightly left. So by the time these winds work their way down to the ocean surface here, you can see, notice how, look at this. Winds are from here, and then at the surface, they are angled a little bit here. So now I've actually got the winds, instead of blowing from 270, as you can see as I zoom in, I've actually got them blowing from 260, and look at the speed. It has dropped. Okay, so the ocean will typically give us about a 10-degree difference through friction in terms of the change in the winds. And remember, that is going to be standard to the left when compared to the upper winds. Now, of course, as we zoom back out, we now want to look at the frictional effects here on, say, terrain or the prairies. So, next slide shows that. You can see here, I've got the geostrophic winds, 270 at 20. Remember, as these winds move closer and closer to the surface, what's going to happen is they're going to spin counterclockwise. They're going to back. So, this vast plain will create more friction than the ocean. So you can see here in the end that it has been deflected more to the left than the winds over the ocean. Here you can see I've got the winds 250 at 10 knots. So here's the winds coming from the ocean, and then as we encounter land, they get bent more due to friction, so from 250. Okay, next up, what we want to do is we want to next look at the winds and what will happen as they encounter this area here where we have the terrain. So let's move on to the next one. Once again, the geostrophic winds here are 270 at 20, but down here, notice because we've got so much roughage in here that the winds have really backed. So let's take a quick look here and see what the actual resultant or what the actual winds are as we encounter the terrain. We can see 230 at 8 knots. So incredibly rough terrain can cause the winds 230 at the surface. It was 270 aloft. It can cause the winds to get bent to the left by as much as 40 degrees. Look at the speed here, how the winds have even slowed down a little bit more. Now, technically, all this terrain will also cause these winds to go up and down and whatnot. We'll talk about that in a few moments, but I'm trying to keep things simple and move to more and more complex items. Okay, so let's take a look now at the final diagram here. We've got the geostrophic winds up here. Remember, standard winds, as we go from a height above the Earth And as we move down towards the surface of the Earth, the winds in every case have backed. Remember that. We made that statement earlier. As we descend, winds tend to decrease in speed because of friction, and they tend to back. We went from 270 to 260 here. Over the terrain, we went from 270 to 250. Over the really rough terrain, we went from 270 to 230. And in every case, I can see 20 knots. Well, over here, 15, over here, 10, and over here, 8. So we've kind of shown that here by superimposing these arrows aloft over the arrows on the surface. Remember, over the ocean, it's going to be about a 10-degree backing. Over the surface of the Earth, where it's not rough terrain, about a 20-degree backing. Over extremely rough terrain, it can be as much as a 40-degree backing. Okay, as we descend, the winds will tend to back. If I was an airplane and I took off, well, I would see that the winds would veer. Now, here's another one that we could get on the exam as well. And let's imagine that I'm a pilot who's maybe flying at, 1,000 AGL, and I'm over the ocean and I'm encountering winds that are 260 at 15. The exam might ask you a question as you're flying towards the coast. What will happen to the wind direction? They could also ask you is maybe you take off from, this terrain area here and you fly towards the ocean. They will ask you the same question. What will the winds do? Okay, pay attention. And I like to draw this little diagram quickly because it helps me remember. Remember, at the ocean, 260 at 15. As it encounters the coast, if I'm flying towards the coast, remember the winds are going to back a little bit more. They're going to get angled to the left. So I would expect an amount less than 260, and there's my 250. I would also expect the winds to slow down. Let's imagine that pilot coming from the other direction. Well, guess what? They're actually going to see the winds veer, because here the winds are from 230. As I come out here, 250, increasing, and now as I get out over the ocean, they're 260 and 15 knots. So Transport Canada can ask you a whole pile of what ifs, and this will happen in the real world too. They'll say, what if you're flying from the coast towards land? What will happen to the winds? Will they veer or will they back? Will they increase or will they decrease? But what if you're coming from land to the ocean? Will they veer or will they back? Will they increase or will they decrease? What if you're going from a high altitude to a lower altitude? Will they veer and back or will they, increase or decrease? But what if you're flying from land in a climb towards the ocean? What will the winds do in that case? So there's just a whole pile of different combinations that they can ask you about what the winds will do as you fly towards the ocean or terrain. Remember as well that they could just simply ask, you are flying in rougher terrain towards smoother terrain. What will the winds do in that case? Lots of combinations based on this diagram here. So don't be afraid to spend a little bit of time to remember it all and to draw it out. Okay, I think that's pretty good for our diagram here on how winds are affected by the surface of the Earth. Right here you can see the statements that I just drew out for you. Okay, so this here, again, you can read this on your own if you want. As I just showed you though through those diagrams, everything that I said in the diagrams is here. I do want to mention this though. Notice this. This is sometimes popping up on the exams as well. Greater surface friction will result in the winds blowing at a greater angle to the isobars. Okay, remember that. That makes sense. And actually, just let me go back for just 1 second here to the iPad, if I may. I don't think my producer was expecting that. There we go. Good switch, real fast. Okay, so remember, isobars here. Look at the angle that the ocean winds make with the isobars. It's very shallow. However, once I get here, we can see isobars, those are going to be the same as parallel to the geostrophic winds, which is going to show, see that huge angle, small angle, huge angle. That will be the same with these isobars up here. Okay, in relation to those isobars. All right, we can go back to the presentation here. Okay, moving on. Now, winds are almost never constant. Usually we can have things pop up like a gust, and this is where there's a sudden increase in wind speed. But don't forget that a gust could also be a sudden change in wind direction. So a gust, technical definition, is a brief, rapid change of wind direction and or speed. This is different from what is known as a squall. A squall is a prolonged change of wind direction and or speed. By definition, a squall must last for a minute or more. Now, be careful, because on the exams you can get tripped up, particularly by this phrase here. Because another use for the word squall in meteorology is the definition of a long line of thunderstorms. This is known as a squall line. So on the exam, when you see the word squall, be careful to take the term in the proper context. Are we talking about a line of thunderstorms, or are we talking about a prolonged change of wind direction and or speed? Now next up, let's talk about something that's a hard to pronounce name, diurnal effects. Okay, when we use this word, what we are saying is the daytime versus nighttime variations. Now, for this little thought experiment, what I want you to do is this. Think about a set of isobars and pressure gradients that are the same nighttime versus daytime. Okay, so we're not going to change those. Surprisingly, what will happen still, though, is that the surface winds will be stronger and gustier during the day as compared to nighttime. All right, we'll come back to this in just a few moments through a drawing as well. You'll see this phrase here that says, at night, a nocturnal inversion develops, and there is no link between the upper and lower surface winds. So the surface winds will tend to back and decrease at night. Okay, I think I'm going to stop there, and I'm going to go right back to the whiteboard, and I'm going to start to draw these effects out for you. Easier to understand than maybe trying to read through this. Let's go to the whiteboard. All right, so let's draw ourselves the surface of the Earth again. We'll draw it from a three-dimensional angle once again. And we'll draw the surface aloft, not the surface, but the aloft zone. So this will look something like this, and then there, we'll go like that, and about there. Okay, so once again, this is going to be, we'll actually say, 2,000 foot level, approximately. So here's what will happen. During the daytime, let's imagine, first of all, right at sunrise. So right at sunrise, we've got the winds that are flowing something like this. And then maybe at the surface, we have some very, very light winds that are flowing from, it doesn't really matter. We'll say maybe a very gentle, gentle breeze coming from almost the southerly direction. So during nighttime, these two winds really aren't connected very well. But as that sun starts to rise, and now we start to get some solar heating going, what's going to happen, as you've seen in the past, is we're going to end up with zones of thermals that are going to start to stretch up
towards the higher levels of the Earth's atmosphere. So, good old thermal here. If I've got a thermal going up, what's going to happen as well is I must have areas where I've got sinking air, right? So it's going to grab this wind and it's going to say, hey, I'm going to pull you down towards the surface with me. So what will happen is this wind that was initially blowing in this direction, now the upper winds get pulled down as well. So that being the case, this wind that was originally blowing this way is now going to end up slowly changing itself to look a little bit more like the winds aloft. And it will actually end up blowing slightly from this direction. Not only that, but it's going to get faster. So what we have is as daytime heating pulls these winds down from aloft down to the bottom, what we have is these winds increasing, and which way did they go? That is definitely a clockwise direction. So during the day, we can say this, during the day, the winds will veer and increase in speed. Meanwhile, of course, nighttime comes along. So the sun sets. Well, guess what happens to our thermals? They start to die. So does this start to die as well. So now those winds become uncoupled. That being the case, well, no longer do we have the upper winds moving down at the surface. So guess what's going to happen? This is now going to disappear, and the winds are going to go back to what they originally were at the surface. So at nighttime, the winds typically back and decrease in speed.
Okay, so what you've seen is there can be a large difference between the upper and lower winds as we move towards nighttime. And as well, you can see that during the daytime, a link is formed between these winds, and that makes them a little bit more similar. Remember, during the day, the winds will tend to veer and increase as those winds connect with one another. As night falls, we will have a decoupling, and what will end up is the winds will back and decrease at night. Although aloft, they can still be really strong. So next up, as for different variations on how winds can move, let's talk a little bit about sea breezes. You see here we've got a nice, warm, sunny day, so a perfect day for you to be out at the beach. But here's what's happening. As that sun beats down on the land and beats down on the water, remember the land will heat up quicker than the water will. So of course that's going to create a column of rising air here. So we're going to have an area of low pressure. Meanwhile, because the air is cooler over the ocean, remember that's going to be sinking. So we've created a pressure gradient. So the air will move from the sea to the land. Then aloft, what will happen is it will move in this direction back towards the high, and we will have that constant circulation. What you need to remember is that during the daytime, if you're sitting here on the beach, the winds tend to flow from the ocean towards the shore. Okay? Of course, nighttime happens, and the reverse will occur. This here is just another diagram showing this motion. You can see the surface towards the shore, aloft, of return out to the ocean. During the nighttime, hello moon, we have the reverse happen. The water is pretty efficient at holding the heat that it's collected during the day. The land will cool down rapidly. So we've got this temperature difference here. It's warm now over the ocean. So of course this air now over the ocean is going to be rising. This air here is more of the sinking air. We've created a pressure gradient, so the wind is going to flow from the shore towards the ocean. So this is what is known as a land breeze. All right, land breeze versus sea breeze. Here's another diagram of the land breeze. Oh, hello moon again. And you can see that circulation going the other way. Now, I jumped ahead for a moment and I moved into what are known now as katabatic winds. Earlier, I mentioned that terrain can have a huge effect on winds in the local sense of the word. In this particular picture here, I've got a mountain that is covered by snow. Down here, I can see nice greenery, so let's look at what could potentially happen in this case. When we have a snow-covered mountain, remember, that's going to create very cold air. They're going to blow downwards into the valley during the day. Whenever we have wind that is flowing downwards a mountain slope, just like this here, those are going to be known as katabatic winds. At night, we can have katabatic winds that will also form, and that's because, of course, we will have radiation cooling, and because of this radiation cooling, whether we have snow at the peaks or not, the overall flow from a mountain will be downwards at night. Now imagine putting these two effects together. A katabatic wind from snow plus a katabatic wind from night radiation, we can get some pretty powerful winds indeed. Now, I know my picture still shows snow on the mountains, but we also want to talk about the anabatic wind. With an anabatic wind, let's say that there wasn't as much snow on this mountain, what will happen is all this bright sunshine can actually warm these slopes and cause the air to start to flow upwards. So an anabatic wind is a wind in the vicinity of mountains that is flowing upwards. So there we go, flowing upwards. Although all this snow might help prevent it in this particular picture. We'll ignore that. Sun-heated slopes cause the air to rise. Now, mountains can have all sorts of effects on modifying wind. I mean, imagine that we have a slope. Well, we're going to move up that slope. Once we get to the other side, we're going to go down that slope. That can create all sorts of rainfall on the windward side. Now, elsewhere on pilottraining.ca, we have a section called Mountain Waves, Winds, and Turbulence. We talk extensively about the effects of topography and winds in that section. So I'm going to kind of go over these slides just a little bit quicker for that reason. There you go, winds associated with mountains. Please check out our Mountain Waves, Winds, and Turbulence section where we'll talk about this in great detail. The next few slides, same statement, wind shear. Okay, we have a section on pilottraining.ca called Wind Shear Types and Causes. So this I'm going to go over a little bit quickly as well. What I want you to remember from this section, however, is that wind shear is defined as a change in wind speed and or direction. A couple of types of wind shear include speed shear and directional shear. Wind blowing at different speeds can create turbulent eddies. Wind blowing in different directions can also create turbulence. Now, just for a moment to show you how this works, let's go back over the whiteboard where I can zoom in a little bit better and give you imaginary examples of different wind speeds and directions. Okay, so let's put my hand in the way here. So what I want you to first of all imagine is my lower hand as being a slow-moving parcel of air, so a slow wind. Meanwhile, my top hand is going to move much quicker. And as I do that, what I want you to observe is what that container in the middle does. So here we go, both parcels of air moving together. Now I have the wind moving aloft a lot faster. Can you see how the air caught between the two wind streams starts to rotate? So that would be an example of speed shear. I could also have directional shear. And in this case, let's imagine one wind, like my hand, going this way, and the top wind moving this way to the left. So if that's the case, what's going to happen again is there you go. You can see that we have a rotation of the air between those two winds. Okay, so there we go. As you can imagine, these winds, if they change, they can have a significant impact on our airplane's performance. We can have a situation where we have what is known as increased performance shear, and we can also have something known as decreased performance shear. Once again, I'm going to get you to look over at that section on wind shear, and we'll go into this in great detail there. Increased performance wind shear is an increase in headwind or a decrease in tailwind. You will need to remember that for the exam, and then you'll need to know about some of the effects of it. Decreased performance wind shear will also affect us, and that's a decreasing headwind or an increasing tailwind. Here's some of the effects of such a situation. Again, I talk about this in great detail in that wind shear presentation. Now, before we close, I do briefly want to talk about Rossby waves and jet streams. When it comes to jet streams, these are winds that are typically at altitudes of about, say, 20 to 28,000 and more. Long ago, as people launched balloons, and in World War I, when they flew airplanes, they discovered that, balloons and airplanes tended to go much faster to the east than they did when returning to the west. And this is partly because, as we've seen, that geostrophic wind, remember, it's constantly forced to the right until the pressure gradient force and Coriolis force equal one another, in which case most of the winds are flowing towards the east. World War II pilots often found themselves being blown off course. They discovered that eastward journeys took much less time than westward journeys. Now, these winds will typically organize themselves into what we call wave patterns, technically referred to as Rossby waves. These are the result of temperature variations and the rotation of the Earth, the Coriolis forces we've seen. Now, these waves help circulate differences in global temperature. Depending on the season and the circulation, there can be from 3 to 6 of these waves at any given time. Now, to see these particular waves, it's usually best that you look at a very high altitude weather chart. You can see here that this is showing us that this is at the 250 hectopascal level. So this is getting very close to 40,000 feet in some situations. Now, as I look closely here, I can first of all see all of these contours. Remember, we talked about how aloft, the Coriolis force forces all of the winds to flow parallel to these contours. From time to time, though, these contours do start to get bends in them. And that's because up here, this is the pole, very cold air here, and then down here we've got warm air. Remember, they're constantly, warm air is trying to push this way, cold air is trying to push this way. And what will happen is we will end up with these bends in that geostrophic wind. It doesn't flow perfectly straight all of the time. So as I look at this diagram, I can actually see a couple of Rossby waves. This is where cold air here, the cold air starts to push downwards. Okay? Cold air here, cold air here. So let's take a look at that. There we go. Just as I pointed out, here's a Rossby wave right here. That's an area where we have what's technically known by a meteorologist as a trough. So cold air pushing down this way. Here's another one here. Here's another one here. And then up here, I can see another one. And the last one's kind of hard to see, but it's somewhere. Looks like there's another one somewhere over here. I'm not entirely sure because I think that's out over Russia, and the weather map doesn't go to that side of the world. Okay, Rossby waves. Now, within these high-speed flows of air, let's look back here. Remember, just like isobars, when we see contours closely packed together, see how tight they are here? And then see how far apart they are here? I would expect the winds to be blowing very strongly here. You can see that we actually have the letter J, and the letter J here where a lot of these contours become extremely packed. See there? We also have a little number here showing how fast those winds are flowing. You can see right through here, I've got what is known as a jet stream. Very fast flowing air through here. Then in through here again, very fast flowing air. Very fast flowing air through here, and then right in through here. These are jet streams. As we've seen, the wind velocities found in the upper tropospheric waves are not uniform, and there are some very fast streams of air that can be found that are associated with them. These high winds are called jet streams, and their speeds can be in excess of 230 kilometers an hour. These jet streams help in the rapid transfer of energy around the globe. And, of course, they can also disperse things, like a volcano goes kablooey. Well, if it gets caught in a jet stream, it's going to get blown downwind at a very high speed, 230 kilometers an hour. They can go all the way around the world within a week. Now, when it comes to jet streams, look at this. 1, 2, 3. Earlier, do you remember how we drew 3 cells in terms of global circulation? If you're thinking that these jet streams are related to the cells that we talked about earlier, you are spot on. So, we have the polar front jet stream, sometimes abbreviated the PFJS. We also have the subtropical jet stream, sometimes abbreviated STJS, and then we have the eastern equatorial jet stream, which is sometimes abbreviated EEJS. Let's look at each one of these in a little bit more detail. But once again, because these can be so complicated, we have a whole section on pilottraining.ca dedicated to just jet streams called jet streams. Okay. First off, the definition of a jet stream. These are very strong high-altitude winds of 60 knots or more. They can be thousands of miles long and hundreds of miles wide. As we've just seen, they are named for the frontal system causing them. The height, latitudinal location, and the speed of a stream varies depending on the season and the temperature. So the polar front jet stream, PFJS, that is typically found between 40 and 60 degrees in both hemispheres. It's found where the polar cell meets the Ferrel cell. This jet stream moves around a lot, and it will bring different weather depending on where it is coming from. So once again here, I can see these contours, and as I look at these contours, look at how packed they are. They're really tightly packed. I can also see this little J just barely hidden in behind these wind barbs. So this is the fastest speed in this particular jet stream. Look at the winds out here, just outside of the jet stream. They're only 15 knots. However, as I move in here to the core of the jet stream, whoa, it looks like 50, 100, 150, 100. It looks like this is close to 180 knots. So these winds here are really just a howling. Yeah, look at that one there too. That looks like 180 knots as well. Those winds are definitely just a howling. With the polar front jet stream, if this jet stream moves south, it's going to drag cold air with it. So that's going to give us stable conditions with high pressure. If the jet stream is pushed north, then what's going to happen is we're going to have warmer air. As this warm air moves in, it can give us strong winds and heavy rainfall. Once it stabilizes north of its initial position, warmer temperatures will prevail and the weather will start to stabilize. So what I'm saying is these jet streams can have a huge effect upon the weather below them. When winter approaches, this jet stream, of course, is going to become stronger and it's going to move southward. Wind speeds in the polar front jet stream are also going to be greater in the winter. So keep these in mind as you write your exam. This is due to the large temperature differences between the polar and Ferrel cells. During the summer, the polar front jet stream will move northward. Remember, this is because temperature variations between the polar cell and Ferrel cell will decrease. So the speeds within this jet stream will also decrease. Again, I'll talk about this in great detail in the section on jet streams. For the subtropical jet stream, the STJS, this is found around 25 degrees to 30 degrees of latitude, which is the boundary between the Ferrel and the Hadley cells. This jet stream tends to move less than the polar jet stream, and it has lower wind velocities than that of the polar front jet stream. The temperature variations between the two cells are not as great as the temperature variations between the polar and the Ferrel cell. And finally, to finish up this section on winds, we have the Eastern Equatorial Jet Stream, the EEJS. This jet stream tends to form aloft at the Intertropical Convergence Zone. This stream is more seasonal and it is associated with the summer monsoons in India. It is a gentle jet stream in terms of winds, and that's because there really isn't all that much of a temperature variation between the circulation cells. Remember, we have that air from the south that's warm, moving towards the equator, and the air from the north that's warm, moving towards the equator. Not much of a temperature difference does not result in a very strong jet stream. Speaking of jet streams, those winds earlier this morning, man, they seem just about as strong as a jet stream. I mean, I've never seen stuff flying around like that in a long, long while. Oh, I forgot. The TAF said they would get strong, but then that they would calm down, but then that they would increase again. Oh no, it's almost that time. Oh, I hear them picking up already. Oh no, it's getting windy again. Really windy. Ah!